Last time we talked about complex numbers, which are numbers of the form x plus jy, where x and y are real numbers and j is imaginary with j squared equal to -1. And we talked about how people didn't really accept the existence of complex numbers because they didn't know how to interpret them. So what finally led to complex numbers gaining general acceptance is when they were interpreted as being points in the plane. Specifically, the complex number x plus jy would correspond to the point xy in the usual xy plane. So if I draw x and a y-axis, and then let's say we have this point with coordinates xy. Instead of thinking of that as an ordered pair, we're going to think of that point as representing instead the complex number x plus jy. So for example, let's draw another set of axes, and let's just consider a couple of complex numbers. So let's start with a complex number which I'll call z1, which is -3 plus j times 2. So if we were to plot this complex number in the plane, the x-coordinate is -3, the y-coordinate is +2. So that point would be -1, -2, -3, +1, +2. So the point z1, or the complex number z1, would be located there in the plane. Maybe take another example real quick. So let's consider a second complex number z2. Let's say z2 was maybe 1 minus j times 4. So we will locate this at the point 1, -4 in the plane. So x-coordinate is 1, the y-coordinate is -4. So the complex number z2 would be located at that point in the complex plane. The number 1 can be thought of as the complex number 1 plus j0. That would correspond to the point 1, 0 in the complex plane. So this point right here would represent the number 1. And similarly, if x is any other real number, we can think of x as being complex by writing it as x plus j times 0. So that will correspond to the point x0, which would be a point on the x-axis. So here we see that the x-axis, or at least the points on the x-axis, represent the real numbers. And hence, people typically refer to the x-axis as the real axis, and they'll usually label it as RE or something like that. As for the y-axis, that's going to correspond to imaginary numbers. So for example, j, we can think of j as being 0 plus j times 1. So therefore, j would correspond to the point 0, 1, which would be located here in the picture. So that point there represents j. And more generally, any other imaginary number or any other multiple of j, you can rewrite it as 0 plus yj. So that would correspond to the point 0y, which would be a point on the y-axis. So points on the y-axis, they correspond to imaginary numbers, multiples of j. And therefore, you usually hear people refer to the y-axis as the imaginary axis when you're working in the complex plane. Introducing some terminology, if z is a complex number, and let's say it's x plus j, y. We say that x is the real part of z, and we say that the number y is the imaginary part of z. So why is it useful to represent complex numbers as points in a plane? One benefit is that we can represent complex numbers by using polar coordinates. So just very quick review of polar coordinates. Remember that if we have a point xy in the plane, we can associate to this point two other coordinate numbers, r, which represents distance to the origin, and theta, which represents the angle that it makes with the positive x-axis, and some equations that relate the rectangular coordinates x and y to the polar coordinates r and theta. We have x is r cosine theta, y is r sine theta. We have r is the square root of x squared plus y squared. And at least in this picture, we can say that theta would be the inverse tangent or arctangent of y over x. A quick cautionary note is note that this formula for theta is not always true, not exactly. So we'll maybe just see an example illustrating how you might need to modify that equation if you want to solve for theta in general. Okay. But if we have a complex number z equals x plus j times y, using polar coordinates, we can say that x is r cosine theta. So we have x plus j times y. And then we know that y is r sine theta in polar coordinates. So therefore, we can also write z as r times cosine theta plus j times sine theta. So all I did there was I took these two r's and I just factored them out of the parentheses there. Now, there is a famous identity. It's known as Euler's identity. And what this identity says is e to the power of j theta is equal to cosine theta plus j sine theta. So at first glance, it's a little bit hard to interpret this equation to see how something like this could possibly be true. We haven't really even talked about what does it mean to have a complex or imaginary number in an exponent yet. And we're actually not really going to touch on that aside from Euler's identity here. This formula, it's most easily explained by doing a little bit of calculus, but as calculus is not a prerequisite for EE 1202, I'm not gonna go into that here. I might do like a short bonus video explaining a little bit why this formula is true, but I'll separate that into another video though. Then we can further rewrite what we have here one more time as z equals r times e to the j theta. Since by Euler's identity, everything here in this parentheses is equal to e to the j theta. This gives us another way of writing out what a complex number is in terms of polar coordinates and using Euler's identity. So between these two ways of representing a complex number, one using rectangular coordinates and one using polar coordinates, in different situations, one of these forms may be more convenient than the other. And we'll see that especially in the next video when we discuss how to do some basic arithmetic involving complex numbers. For now, let's do a few examples of switching between rectangular and polar representations of complex numbers. So let's start with the complex number z equals, let's do minus 5 minus j times 12. So what we're going to do is we're going to rewrite this complex number z into the r e to the j data form using the polar coordinates. Now it's not super important, but for problems like this, I like to draw a picture. It just helps me visualize the problem. So this point z, it has an x-coordinate of -5, and it has a y-coordinate or an imaginary part of -12. So as a point in the plane, it would be located somewhere here in the third quadrant. And maybe since I'm working with complex numbers, it might be better to write this as negative j times, or j times -12, since this is the imaginary axis. This is the real axis. What we need to figure out is r and theta, the polar coordinates of this point here. So r is this distance between the point and the origin. And remember that we can solve for r by simply doing the Pythagorean theorem. So r should be the square root of x squared plus y squared. X is -5, and y is -12 technically. So this will give us the square root of 25 plus 144. And using a calculator, you can find that this will give you 13. So we have r. Now what we also need is to find theta. So remember that for polar coordinates, we measure theta from the positive x-axis. So we want to find what is this angle here. And to find that angle, what we can do is we start by finding what this little angle is. So we've got a right triangle in the picture here. I'm going to redraw that triangle separately down here. So it looks something like that. We saw that r, the hypotenuse, has a length of 13. This side has a length of 5, and this side has a length of 12. So what we're going to do first is we're going to calculate this angle here. Let me give this angle a name. I'll call it alpha. So we know from trigonometry that tangent of the angle alpha should be equal to the opposite over the adjacent. So therefore, we can solve for alpha as being the inverse tangent of 12 over 5, which, using a calculator, see here, if we round it to 2 decimal places, that turns out to be about 67.38 degrees. If we want it in terms of radians, it's about 1.176 radians. Now coming back up here to the picture though, notice that this angle alpha, it's not the same as the angle theta that we were looking for, but hopefully you can see that theta should be 180 degrees plus the additional angle alpha. So therefore we can say that theta, in terms of degrees, it's 180 degrees plus 67.38 degrees, which will give us a total of 247.38 degrees. So now that we've calculated r and theta, we can now rewrite the number z into the complex exponential form here. So we have z is r e to the j theta. We found that r is 13 and theta is 247.38 degrees. So real quick, as an alternative, we also could have used this angle here, but remember that if you're measuring clockwise from the positive x-axis, you have to consider that angle to be negative when working with polar coordinates. So for instance, here in the picture, this total angle is 180 degrees. So if we do 180 minus alpha, that should give us the green angle here. So the green angle, in terms of degrees, it should be 180 degrees minus 67.38 degrees. But then since we're measuring this angle clockwise from the x-axis, we should actually consider it negative as well. So I'll put a minus in front of all of that. And then if we subtract these from each other, you should get 112.62 degrees negative. So an alternative answer to this question, using r as 13, and then using an angle of negative 112.62 degrees, this would be another acceptable answer to the question. So let's look at another example. Let's consider a complex number z. And let's say this time this number is in the complex exponential form now. And let's use radians instead of degrees for this problem. And let's say we want to convert this complex number into the rectangular format. So we want to write it in the form x plus jy. So to do that, we have z in the r e to the j data form. So we already know the polar coordinates of this point. R is 4, data is 2 pi over 3. Let's draw a little picture first, just to see where is this complex number in the complex plane. So remember that r represents distance from the origin, and theta is the angle from the positive x-axis. Because r is 4, we know that this complex number is going to be located somewhere on a circle of radius 4. So let me just kind of draw a circle here. So let's say this is a circle of radius 4 here. Now the angle is 2 pi over 3. So 2 pi over 3, that's going to be an angle in the second quadrant. If you're not too familiar with radians, this is the same as 120 degrees, because pi over 3 is 60 degrees. So 2 pi over 3 is 2 times 60 degrees, so it's 120 degrees. So 120 degrees is more than 90 degrees, so it's going to be somewhere around here or so. So then this point here, that would be our complex number z. So since it is located in the second quadrant, the x coordinate, or the real part, should be a negative number because it's on the left half of the plane. The imaginary part, or the y coordinate, should be positive because it's in the upper half. Now to calculate the x and the y coordinates, or the real and the imaginary parts, we really just need to use these formulas. X is r cosine theta, y is r sine theta. So we know r is 4, theta is 2 pi over 3 radians. And then using our knowledge of the unit circle, cosine of 2 pi over 3 is equal to negative 1/2. So this will be equal to negative 2 altogether. Y is r sine theta, r is 4, theta is 2 pi over 3. And then sine of 2 pi over 3, that's going to be equal to root 3 over 2. And then here we can simplify that. 4 over 2 is 2, so it gives you 2 times square root of 3. So now that we have the real and the imaginary parts, we can rewrite our complex number z as x plus j times y. Now let's look at just a few more examples real quick. So let's consider the complex number 1, and maybe just to emphasize that we're thinking of it as a complex number, we can write it as 1 plus j times 0. So we know that's 1 is a real number, so it's going to lie on the real axis here. It's the point 1, 0. Okay, so if we want to rewrite into the r e to the j data form, r is distance to the origin. So this distance here, well, we know that that distance is 1, since this is really the point 1, 0 in terms of the x and the y coordinates. As for data, remember that data is measured from the positive x-axis and then outwards, but for a point that's already on the x-axis, the angle data would be 0 degrees or 0 radians. So that means we could rewrite the number 1 using the polar coordinates. R is 1 and data is 0. And that's maybe not too surprising because you may remember that any number raised to a power of 0 is considered equal to 1. So e to the 0 is 1, and then 1 times 1 gives you 1. So this equation looks consistent, so it looks good. Another possible angle for this point is 2 pi. If you think about going around the circle once, you get an angle of 2 pi there. So you can also write the number 1 as 1 times e to the power j times 2 pi as well. Let's look at z equals j next. So let's emphasize that it's a complex number by writing it as 0 plus j times 1. So this is going to be on the imaginary axis. And as the point 0, 1, we know that this distance, that distance from the point to the origin, is 1. And for a point on the positive x-axis, that would correspond to an angle of pi over 2, or 90 degrees. So in terms of the complex exponential using polar coordinates, j, you could write it as r is 1 times e to the j theta, where theta is pi over 2. Or I guess if you use degrees, you could also do 90 degrees. All right, I'm going to end the video with that.